Bienvenue à Louvain-la-Neuve. We are in rainy Belgium today for a new episode of MoCapLab TALKS. We are interviewing a very inspiring biomechanist and inventor today. Our guest is a part of a team that founded a spin-off company from this lab that develops very innovative products for the biomechanics research environment. Some of the products made it even into space.
Let's welcome Massimo Penta.
Thank you.
Thank you for having us, Massimo. It's a great research environment here. Can you share what kind of research you and the team here at the faculty conduct in this lab?
Okay, so in the lab here, it's the lab of locomotion and biomechanics. So we study essentially locomotion, that means walking and running, a little bit of jumping as well. Basically, we explore here the biomechanics of the pendular mechanism of walking, the spring mechanism of running, but across essentially different type of paradigms. For instance, we study the evolution of this mechanism with age in children. We've studied the mechanism in different size animals. For instance, we've studied the locomotion of elephants. Mm-hmm. We studied this mechanism in different situations like load carrying. We've studied the load carrying in African women, in the most famous porters in the world, which are the Nepalese porters, as you might know. We studied the evolution of this mechanism with altered gravity. So this obviously does not happen in the lab, mm-hmm. but we do this in parabolic flights. And we also have developed a system that allows to simulate gravity in a weightless environment like the International Space Station.
Okay, that's quite a broad variety of applications.
Yes.
What is your specific role in the faculty and in the organization of the research?
Okay. So initially, when I started in the lab, this is about 25 years ago, I was here for my master thesis, and I specifically looked into load carrying in African women. But after that, I did my PhD in a slightly different domain, and I came back to the lab, let's say, more as a technology supplier or a technology support, helping the members of the lab to develop the instruments they need to carry out their research. Typically, I help the lab to develop instruments like force plates, like instrumented treadmills, systems to study the jump or the motor control of the reception from a jump. We have developed EMG as well. And now we've turning this expertise in developing new systems into new products that we are also selling as a spin-off now. Mm-hmm.
I was revealing that in the beginning of the video. You are very passionate about biomechanics and technology, and that passion motivated you and your colleagues to start a technology spin-off from the university. As you just mentioned, what is it all about?
So our initial idea about developing equipment is born due to the fact that the type of equipment we needed for our research was generally not available on the market. We could not find a force plate that could bear the weight of an elephant, for instance. So we had to design our own force plate. And the same goes for other things. When we wanted to get an instrumented treadmill, this type of equipment did not exist or were too expensive for us. So our idea was, if we can develop these equipment for ourselves, then we could probably also develop it for a broader research market. So essentially, Arsalis, which is our spin-off company, develops this type of products for research laboratories. We typically specialize in developing one-of-a-kind type equipment, but nowadays, after a little bit less than 15 years of activity, we're also spreading our production to more standard products like the system that you see here at our back, which is an instrumented treadmill.
What does it take to develop such a product?
Well, we've had the opportunity to develop a few systems for the aerospace business where the regulations are much more, let's say, high level or much more difficult to achieve. And this gave us a very strict methodology in the development of our products. For instance, all our design need to be validated, all our productions need to be made according to a given procedure, all our products need to be tested, 100% of our production is tested. So it takes a whole logistic and organizational process to be in place in order to be able to produce this type of, I would say, high reliability products. Then the other good thing, the other important thing is that you need a market, or you need some interest for that type of product. And this is where we, let's say, feed also the market with our research activity by, let's say, supporting the applications of our product through our research activity.
You are testing the device here at the moment. It's a prototype for a new treadmill that you are developing with a well-known treadmill manufacturer. There's a very interesting biomechanical feature that you developed. What is it?
Yes, okay, so this treadmill is a new version of our small size treadmill. It's a treadmill, it's the Pluto model from company HP Cosmos. And the instrumentation we are doing here is to mount load cells underneath the treadmill so that we can measure the ground reaction forces applied when the subject is walking or running on the treadmill. A very important feature of the system is that while walking, you have this, what we call the double stance phase. That means you're standing on both legs at once. Now you have only one set of sensors in this treadmill. So we have developed an algorithm that allows you to split the part of the total force that is applied by the left leg and the part that is applied by the right leg during this double stance phase. And this allows to be able to calculate the force that is under each leg in 3 directions, to be able to also do analysis like inverse dynamics or joint torques measurement that require the researcher to know the force under each leg.
So that means you can also combine this treadmill with motion capture.
So you can combine the treadmill with motion capture, but not only. Of course, you can combine with EMG. We also have another option that combines it with a pressure measurement that allows you to really measure the roll-off of the foot on the floor during this double stance or single stance phase.
Plus 3-dimensional forces.
Plus 3-dimensional forces, which bring not only the high speed change in the force, which is not part of the pressure signal, but also the lateral and the fore-aft propulsion force that is required for walking forward or running forward.
Complex product.
That's what we do.
Did you start the research or the idea for the product or prototype first?
Okay, our interest into these instrumented treadmill comes from our research questions. Initially, we've developed force plates, but pretty soon for our applications, the space would become too small, and we had to collect a large number of steps, which means a large number of back and forth trials. So to avoid this, we found the possibility to instrument a treadmill. We tested different types of treadmills, and the one that would meet our quality standard was this treadmill by HP Cosmos. It was not this model, but it was an older model, and this allowed us to make our first records for the gravity simulator, in fact, which is now more than 15 years back. And well, from this interest in research, we discovered that this product could also interest other research labs, and we turned this after into a standard product.
This basically leads me to my next question. Who would benefit from such a product?
Well,
it's a research-based product.
Yes. Well, the main interest of the product, I would say, is threefold. The first is for research and to improve science, let's say, to improve the knowledge of locomotion, the knowledge of the biomechanics of walking and running. Also, second application is for the clinics, so it will benefit patients who will have an impaired walking, especially, and or will be able to relearn how to walk after an injury or trauma. Or the third fold of this application is, of course, in sports, where we could develop, let's say, feedback or biofeedback tools to help athletes gaining performance or follow their performance or recover, let's say, after an injury, for them to go back to the field with the best, let's say, recovery, or the best way to monitor their recovery after an injury.
You have already developed products that found their way into aerospace.
Yes.
That's amazing.
That was a very fun experience, yes.
What was it?
Well, we were asked to develop a system that could simulate gravity or reproduce gravity when an astronaut is running up in the International Space Station. Basically, you know that astronauts have to do some exercise to avoid the deconditioning of their bones and muscles during their long stay in microgravity. And well, to make the running happen, you need a force that pulls you down to the floor. And this force is not present in weightlessness. So we had to generate a system that could replace the existing bungees that they use in the station. So this was asked by NASA to us, given our expertise in the development of this type of one-of-a-kind type devices. And we were involved into something like a 10-year process to develop several versions of this subject loading system that can create a vertical force that pulls the subject down with a force that is equal or proportional to his body weight, like 20% body weight, 40% body weight, 60%, or even 100% body weight, to allow them to exercise during their flight in ISS.
Because our body needs gravity in order to maintain certain biological functions.
Not only, but also for running. To run, you need a force that pulls you down to the floor after each step. Otherwise, you push on your back leg and you will never find the floor again. So to make the exercise happen, and the exercise is the thing that will stimulate your bone mass reconstruction and your muscle mass reconstruction. So to allow this exercise, you need gravity to make this possible.
That were actually my 8 questions, but I have a little bonus question. I'm very curious. There was this very, very amazing, interesting fun fact that I mentioned in the beginning. And the whole lab has been transferred to the Kumba Valley on the way to the Mount Everest.
That's right.
Some years ago, including researchers, students, and equipment. That's terrific. What did you guys do there with all the equipment in the Himalaya?
Yes. So basically the idea there was to study how these porters, you know, they're the most famous porters in the world, they are used to carry weights that are impressive. They carry more than half of their body weight. Some of them carry even more than 100% of their own body weight on their back. And this is all supported by a strap across their head. And they carry these weights on their way to Mount Everest, not to go up the mountain, but at an altitude of just less than 4,000 meters. There is this big market in a town called Namche Bazaar. Every week there is the market, but everything that is sold on the market comes there carried by a human. Okay, so you imagine food, cloth, energy in the containers of kerosene. All this is carried by humans. So we moved the whole lab, including force plates, motion tracking system, VO2 measurement systems, to study how possible this exercise was for these porters. We recruited porters on their way to the market to stop by our lab that was installed there for about 4 months. We recruited them to walk, do their exercise in our lab, and then continue their way to the market, either going uphill to the market or going downhill after the market.
What was the main outcome? Can you summarize?
We found that these porters have a very efficient way to carry these loads. So they managed to save some energy. If you and me would carry, let's say, 20% of our body weight, it would cost us 20% of energy consumption in addition to what we consume without weight. Well, they can carry 20% for free. That's the first thing.
And free luggage, so to say.
It's free luggage for them. And if they carry more than 20%, instead of increasing proportionally to the weight, it increases with a proportion that is less than 1 to the weight. Now, how this exactly happens, we still don't know. So we know that they have improved the efficiency of their production of mechanical work, but the question remains open of how exactly they manage to increase their muscle efficiency.
Massimo, thanks a lot for having us here in UCLouvain. UCLouvain,
right?
That's I'm learning, improving my French. It was super great to have.
Thank you for your visit. It was a very great pleasure for me too.
Thank you. If you like this interview and you want to see more interviews like that, hit the subscribe button, click the notification bell in order to get a notification every time we upload a new video. See you next time.
UCLouvain.
UCLouvain in
UCLouvain.
La Neuve.
UCLouvain.
I have no idea.